Oh, one more questions. 1.233 would be.
And then can we do 3?
Yeah.
Because there's no answer to that.
1 point what?
1.2 number 33. It's one of those applied.
1.233?
Yes.
Okay.
On
All right.
Can you do 38 after
So
that?
then work on this 34. Okay, so number 33 and 1.2. So on planet G, ZYX, a ball dropped from a height of 20 feet. A ball dropped from a height of 20 feet hits the ground in 2 seconds. If a ball is dropped from the top of a 200-foot tall building on the same planet, how long will it take to hit the ground? And with what speed would it hit? Okay, so a ball dropped from a height of 20 feet hits the ground in 2 seconds. How do we start this off? It's a plan. Is it YVX, GYX, whatever? What's the constant force of acceleration? We don't know.
It's going to be in this case a negative G.
It's just going to be some constant. I'm going to call it C if we assume that it has constant acceleration due to gravity, right? Now it should be negative. All we know is that it hits the ground in 2 seconds from a height of 20 feet. Right. All right, so if this is the acceleration on the planet, and it's a constant, we know C will be negative. And so I don't need to put the negative there and say it's going to C is positive. Let's just call it C and say we know that C is going to be negative, downward. Then the equation or the formula for velocity would be what?
CT plus another.
Plus a V naught.
CT plus V naught, where V naught, if you put in 0, you just get V naught, which corresponds to the initial velocity, right? Oops, not G. V of 0, velocity times 0 would just be V naught. But what can we assume about it if the ball is dropped?
V naught should be 0.
Yes, yes. If the ball is dropped, then we take V naught to be 0. Ball dropped. Okay, so our V of t equals CT. That's velocity. And it tells us that, what's this like? 32, no. Wait, was this 30? You asked 33. Yeah. Ball dropped, 200. Ball hits the ground in 2 seconds. We know that. Okay. So give me the height function, or the height, or the vertical displacement, whatever you want to call it.
CT squared.
Over 2 plus
Some
H naught, where at time 0, that's a constant. So
ages.
that represents initial height at time 0, and we know that to be 20. Okay. We know one other piece of information. It hits the ground in 2 seconds. So that is a crucial piece of information. I know that when t is 2, we get, on one hand, I'm just going to put the 2 in there, square it, we get 4 over 2, so that's just going to be 2 times c plus 20. We know something about that. The object hits the ground, so after 2 seconds, its height is simply 0. So this is, it's like one of these versions of that last long example we had. We've got all these things, we have to play a little bit of detective work. In this case, it's the height function that we need to solve. We know that the height is 0 after 2 seconds. This equation is what's going to allow us to solve for the unknown constant c, which we take to be the acceleration. So, right, well, what's it going to be? C is going to be negative 20 over 2 or negative 10. And that represents the force of acceleration. Notice we didn't need the force to be negative. We know that it should come out negative like it did. And this would be in what units? Yeah, feet per second squared, just for brevity. Feet per second per second. So now we know that. Good. We know some important things, because when we then go to what, 200-foot tall building, says, how long will it take to hit the ground? Okay. So now the 200-foot building. We can reuse a lot of this because we're on the same planet. Remember the last one we talked about, oh, a woman jumps this high on the Earth, how high does she jump on the moon? Two different gravitational constants, acceleration. This is on the same planet, so we could use this, right? In fact, I could use this as well. Now we know that C is -10. Right? That's our C. And we also know that the height function would then be -10. Antiderivative of velocity will give me the vertical height. -10 t squared over 2 plus v naught t plus h naught. Where v naught, again, if the ball is dropped, that is 0. And h naught is the initial height, and if it's dropped from a 200-foot tall building, that's 200. We got everything we need. Now it says 2 questions. How long will it take to hit the ground?
Say t equals 0, so okay.
When the height is exactly 0. So, solving that, get the 5t squared to the other side. 5t squared would have to be 200. So t squared would be equal to, what's that, divided by 5? 40. Right, divided by 10, that's too much. That's 20 times 2 is 40. So what would the time be? Yeah. Which is 4 times 10, 2 root 10. Yeah, what is that, roughly? 6.32 seconds. Okay, good. And then we could use, the velocity function to tell the speed when it hits the ground. So the velocity at impact, in other words, we want to know the speed that it attains right at the moment it hits the ground after 6.32 seconds. So we're just going to plug in the velocity function right here. And it's dropping 10 feet per second each second. So every one of those 6 seconds, it increases its velocity by 10 feet per second. Yeah. So velocity at 6.32, well, -10 times t. So what, -63.2 feet per second? Okay. Negative means it's directed downward. If they ask for, did they ask for the speed? Speed is just the magnitude of the velocity, absolute value of velocity, so 63.2 feet per second.
Right. How long and speed?
Velocity has a direction and
Yeah, and if it's rectilinear motion, right, the motion can be directed straight up or straight down. Those are our 2 options. So if it was by a vector, right, I vector, or the k vector, really, -k. So that gives the direction as well. So either forward or up or down. So the sign just means it's coming downward, directed velocity, but the speed is 63.2. Speed is the absolute value of velocity, so we get 63.2 feet per second. So a little detective work again with those, different anti-differentiating. Okay? And knowing where we can find the information that we need. In this case, in the height function, because they tell us how long it takes to hit the ground. And you had another question?
Yeah, 38, but I checked with my peers and we got the same answer. So if we're running short on time, that's okay.
Yeah. That was interesting units because you're talking 60 miles an hour, that's speed. The acceleration is a weird unit. Okay, so velocity they give you miles per hour, which is nice when you're driving a car. Now, the derivative of that velocity is acceleration. It would be measured in what? Miles per hour per hour. And that's a very strange unit of measurement, miles per hour, because that's not very good if I'm only driving for 10 minutes or something.
Yeah.
Miles per hour. Usually it's in things like feet per second, or meter per second. You know, things that are very precise. Miles per hour.
Dimensional analysis.
It's a very coarse measurement, you know. It would be like measuring the duration of a, I don't know, a synapse firing using hours. 0.000032 hours or something, you know. So not a very good measurement of acceleration when we're talking about a short period of time or something. Okay, so anything else? All right. So we might be without service. This computer is so strict. They have all the stuff that is set up here. They don't want anything to get any viruses. I can't undo the security settings to do what I want to do with it, but we'll work with it. Okay. So, quick example, while this warms up, another 15 seconds. We're going to be looking at this differential equation, very basic one, first order differential equation, and also integrable. dy dx equals 3x squared. Yeah? So again, it's only a function, the expression on the right of that differential equation is a function of only one variable. In fact, the independent variable. And that's the kind you can solve in Calc 2, right? Anti-differentiation. In fact, there's a section in Calc 1 where you talk about finding anti-derivatives. Okay, so this is an example of an integrable equation. Involves only x, the independent variable. We'll also see differential equations that only involve the dependent variable, y. That'll be a little bit different situation. But what is the solution to this? Y of x, if we use function notation.
X.
Yeah. We just integrate the right side, 3x squared with respect to x, and we get what?
X cubed plus constant.
X cubed plus a constant of integration if we're talking about the general solution. Any value of c, any constant, would satisfy that differential equation. We have no further information to know what the specific value of the constant needs to be. So what is this graph, what would the graph of that look like? So for instance, if c is 0, what does this graph look like? Cube? The cube function? Right, it's the cube function. Okay. So x cubed plus c, if c is 0, and I'm going to use a weird little scale here, if that's 1 and that's 2, well, that's a little bit off the chart right now, but it's going to come up and increase very quickly, yeah? -1, 1, 2, -2. And the other side, same thing. And try and draw this as accurately as possible. Something like that. Okay. So this one is if c is equal to 0, is that right? Now, if c is equal to 1, what does it look like? Right, just a vertical shift. And that would be right there. Okay, so green is if c equals 1. And let's do one more. If c were equal to -2, just be the same thing, but shifted down. So like we talked about last time, these in a way are all parallel to each other. Okay? So what we notice about the slope, well, the form of this differential equation, dy dx, this first order derivative, just means the slope of the curve. the slope of the tangent line. So you notice that at any x, the slope of the tangent line is the same. Yeah, that's all a vertical translation does. It changes the vertical placement of the graph, but it doesn't change the slope of the tangent line. So all these curves have the same slope, and I could just keep going, right? At any x, they'd have to have the same slope. I'm trying to keep that the same. At 0, what is the slope of all these curves?
0.
dy dx. If I put in 0, I get 0. So these all have a slope of 0. So we can represent that slope with little line segments. In fact, dy dx is just 3 times x squared. When x is negative 1, 3 times negative 1 squared gives me 3 again. And so these guys all share a slope of 3. Now it doesn't look like 3 because my scale is a little bit wacky on the y-axis. I had to make it bigger. Right? And at 2, it's very steep. The graph would be, well, 2 squared says dy dx. 2 squared is 4 times 3 is 12. At x equals 2, we'd have very steep segments. So a first order differential equation of the form dy dx tells us some information about the slope of the tangent line of the curve at a particular point in the xy plane. Right? So I'll write it this way. The slope depends on x only, in this case. So in fact, the dy dx gives the slope of the tangent line to the curve. To the solution curve, not just any curve, but the solution curve at any point x. So we can draw these little line segments, right? Tell us the slope of the tangent line at any value of x. It says follow that slope, and that's the way the curve has to go. So drawing little line segments, dy dx tells us the slope of the tangent line, and it's equal to 3 times whatever x is squared. If we draw little segments, right, with that slope, then we create what's called a direction field, or slope field of that differential equation. Okay? In this case, it depends only on x, so we see that the slope is same for any x value. So vertical columns all have the same slope. Okay? But that doesn't always have to be the case. So direction field of a differential equation is what we're going to be talking about. Okay? And it's a graphical technique. Now, in this case, this equation is so simple that we don't really need to depend on a slope field to know what it looks like, because I can find an explicit solution, right? Y equals x cubed plus c, right? I don't need to have a slope field. However, in general, solutions may not be so easy to find, and I mean algebraic solutions. It's often very tricky or impossible to solve a differential equation exactly. So by exactly meaning an algebraic solution, so a formula. Okay. So sometimes we have to resort to what's called more indirect methods. So indirect methods to approximate the solution to a differential equation. All right. So there's, there's a graphical, that's what we're talking about today. And there are multiple numerical ways to generate approximate solutions. Okay? And by solutions, we're talking about curves, functions that satisfy a differential equation. Okay, so graphical and numerical. Today we're going to be talking about one graphical approach. Okay? So, here's the general idea behind it. Now, our first example, we have an integrable differential equation. Okay, one that involves only x on the right side. That doesn't always have to be the case at all. So the general theory, if we're given a first order dy dx, that's what tells the slope of a curve at a point. So a first order differential equation of the form y prime or dy dx equals, and some function involving x and y, or maybe just one of them. First order differential equation like this tells us, this expression tells us the slope of the curve dy dx at any point. So at any point, x, y in the plane. All right. So we calculate this value, calculate y prime, for at several different points, usually a whole grid. Okay, at several points, and we represent them in the plane as short line segments to represent the slope. That's an L, line segments. Sorry, when I try and write and think ahead at the same time, bad things happen. Okay, so we represent them as short line segments, and this is what this generates what we call the direction field. Associated with that equation. Okay? So let's actually do one. Let's do one by hand. Okay? And then we'll all be wise about why we never do them by hand. Okay? So, but it's helpful to illustrate what it represents. Okay? How they're generated. So let's sketch the direction field. DIR. So the direction field for the following differential equation. dy dx equals, say, x minus 2y. So this one, not integrable in the sense that it involves only the independent variable, right? That would be simple. It would be x squared over 2 plus c. But it also involves y. So this says that the slope of the tangent line of the curve that we're looking for, the slope of the tangent line at any point x, y involves both x and y, but I can calculate it, okay? At what's called, at a bunch of different points in the xy plane. So let's generate a little table. Okay, so over here we're going to have our x values. Over here are y values. And we're going to do it fairly small. -2, -1, 0, 1, and 2 for y. Okay. And for x, well, we'll do the same grid. -2, -1, 0, 1, x equal 2. Okay, that should give us a good look at this. Now, the way we're going to generate this, and use pencil because arithmetic all day. At any point xy, dy dx is calculated as x minus 2y. So for instance, let's start off with an easy one. At the point 0, 0, dy dx would just be 0. I'm plugging in 0 for both. I love zeros there, yeah. Now, if x is 0, for instance, and y is 1, then it's 0 minus 2 times 1. Right? That's 0 minus 2, we get negative 2. Okay? If it's at the point 0 for x, 2 for y, so 0, 2, what do we get? 0 minus 2 times 2, that's 0 minus 4, negative 4. And this is linear in both x and y. If you fix x at 0, it's just negative 2 times y. So negative 2 times negative 2, that's 4. When y is negative 1, negative 2 times negative 1 is negative 2. You see the slope decreasing across that row. Oh, yeah, sorry. Negative 2. Okay. So when x and y are both negative 2, let's just find some of these values. Negative 2 minus 2 times negative 2, that's going to be negative 2 minus negative 4. That's negative 2 plus 4. That gives me 2. No, wait, negative 2, yeah, gives 2. Negative 2, negative 1, 0. Negative 2, 0, negative 2. You can see that for a fixed value of x, these are just decreasing all the way across. So just for the sake of time, we'll just calculate the first in the row. When x is negative 1 and y is negative 2, we got negative 1 minus negative 4, so that's negative 1 plus 4, we get 3. Negative 1. Oops. That's a positive 1. This is why you do, yeah, just arithmetic. That's negative 1, that's negative 3, that's negative 5. Okay. When x is 1, y is negative 2, we got 1 minus negative 4, that would be 5. Now notice the pattern also in the columns. If x is 2 and y is negative 2, I got 2 minus negative 4, that's 6. So they increase by 1 this way, because it's also linear when we fix y. Yeah. So 0, 1, 2, that's going to be 3 and 4. Negative 2, negative 1, 0, 1, 2. Negative 4, negative 3, negative 2, negative 1, 0. Negative 6, negative 5, negative 4, negative 3, and negative 2. Now what do I do with all those values? Yeah, we're not graphing those numbers, but those numbers represent the slope. Okay, broad line, straight edge here. 1, 2, it's going to be pretty small. 1, 2, negative 1, negative 2, negative 1, negative 2. Okay, so when x is 0, and let's see, when x is 0 and y is 4, and y is negative 2, we have a slope, a line segment of slope 4. What I'm going to do is just fix an x value and then go along all the y values. Okay, so with x fixed at positive 2, at negative 2 for y, right down here, 2, negative 2, we got a slope, line segment of slope 6.
Push it up.
There we go. With x being 2 and y being negative 1, right here, we draw a line segment of slope 4. It's hard to eyeball these. And 2, 0, it's a slope of 2. That's doable. And then at the point 2, 1, it's slope of 0. So I'm just representing these with a line segment. And at the point 2, 2, we have a negative 2. Okay. All right, now when x is 1 and y is starting at negative 2, we get a slope of 5, very steep. And when x is x is 1 and y is negative 1, we got a 3. When x is 1 and y is 0, we got a slope of 1. Okay. And when x is 1 and y is 1, we get a slope of negative 1. So these line segments, these values here represent the slope of the tangent line at that point, at negative 3. Okay? When x is 0, starting at y equals negative 2, we get 4. Then 2. Then 0 again. Then negative 2. Then negative 4. Okay. When x is negative 1, and starting at y equals negative 2, we have a line segment slope 3. You can eyeball those a little bit, like thinking of rise over run. Then a slope of 1. Then a slope of negative 1 when y is 0. Then a negative 3. And when y is 2, a negative 5. Okay. And finally, when x is negative 2 and y is negative 2, we get a slope, line segment slope 2, 0, negative 2, negative 4, and negative 6. All right, so that's our tiny little slope field. Okay? And you can see it's computation heavy, right? Okay. And the fact that, we can only do so many computations, even from negative 2 to 2 in both directions, we have to do 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 25 little calculations. Okay? All right, but it gives you a general idea of how it works. Okay? Now, say with this example, say that we're given an initial condition that y of 0 equals 1. So this is our slope field. Could you then approximate what the curve looks like? If y of 0 equals 1, that gives us a point. It drops a point into this slope field. Well, right at that instant, the curve at 0, 1, 0, 1 has a slope of negative 2. So it tells me that it has to be going off in that direction at that instant. Okay, so we go off in that direction for a moment, and then recalculate, not literally, but with our minds, and we follow these as best we can. Oh, that one's 0. That one was positive. Oh no, wait. What's going on at 1, 1?
Negative 3.
What? So does it go that far, but then it turns and then it flattens out? See, they're not too exact when you do them by hand because you only got a whole number.
Looks like it's pushing towards like a It's the Euclidean solution.
What's that?
Pushing it towards that flat spot and everything.
So somewhere it has to have a 0. Right. X minus 2 right equals 0.